Hello everyone, welcome to another video, and in this one we are talking about vector embeddings or word embeddings, a practical approach. So we have talked about large language model before a lot, and we have built multiple agents. If you are keeping up with the AI Engineering 101 playlist, we have covered a lot of videos in this playlist on AI engineering, agentic workflows, and optimization. This is yet another episode, and here we will be talking about vector embeddings, or we also call it in the NLP world as word embeddings. Now, before moving ahead, let's talk about what actually word embeddings are. So you can think of this as a stream of numbers, or we can also call them as vectors. So these vectors are real numbers which can be represented by digits and decimals, and you can think of this as every word or a character can be represented by a series of numbers, and each and every series represents a particular word uniquely in a high dimensional space. So you can think of this diagram given here. Here, the thing is, we have a lot of words: cat, kitten, dog, houses, man, women, king, queen. And you see all of these words are represented by a stream of numbers, or we also call them as vectors. And these are called vector embeddings. And since this represents a particular words, it is also known as word embeddings. Now, the number of numbers or the number of vectors representing each word is called the dimension of an embedding. So for this particular image, you can think of this vector embedding having a dimension of 1, 2, 3, 4, 5, 6, 7. So you can think of this as a seven-dimensional vector embedding representing each word in a seven-dimensional hyperspace, and it is represented by a series of 7 vectors or 7 real numbers. Now the interesting thing to note is this is one of the vector embeddings which has been trained on a deep neural network, and since this has been trained through a deep neural network on a large corpus of text, this understands the semantics. So this understands what a particular word means, and if two words are similar, the embeddings have the capability to place them close together in a particular space. So you can think of this as a 7-dimensional hyperspace, and this particular embedding is trying to keep the similar words closer in the embedding space. So this example, cat, kitten, dog, house, you can see cat, kitten, and dog. All of 3 words are pet and they are closer. That's why on the right side in the higher dimensional space, cat, kitten, and dog are placed closer, while the house is, this word is, it's a non-living object and it is way different from cat, kitten, and dog. That's why it is represented away in a distant place in a dimensional space. So the thing is, this is a 7-dimensional vector embedding, and you obviously know that there is no way to visualize more than 3 dimensions. And to make things easier, what we do is that we perform dimensionality reduction. So if we want to visualize a 7-dimensional embedding, we try to reduce it to a 2-dimensional embedding, keeping the information without losing the information, and then trying to visualize it in a 2-dimensional space. So you can think here what happened is the dimensionality reduction has happened, and it has converted the embeddings from 7-dimensional to 2 dimensions, and hence you can see dog, cat, and kitten are at a common place closed together, while houses are kept away from these words because the semantic meaning of houses is a bit away from these dog, cat, and kitten. One more interesting thing to note is here man, women, king, and queen are also determined by a series of numbers or vectors, and once we reduce the dimensions of this embedding from 7 dimension to 2 dimension, you can see that the embedding also maps the relationship between two words very accurately. So you can think here the way man is related to a woman is similar to a king is related to a queen, and that is why the distance between man and women in the higher dimensional space is equivalent to the distance between the king and the queen in the same higher dimensional space. So this is what we are trying to showcase here. The distance between man and woman is equivalent to the distance between the king and queen. And this is pretty much what a vector embedding or a word embedding is in the world of natural language processing. Now, as a part of this video, what we're gonna do is that we're gonna talk more about Gemini Google word embeddings, which are obviously trained on the Gemini models. We'll see how you can practically pull those models and use that in your own Python notebook, and you can fetch the word embeddings for a word or a phrase or a sentence from that embedding model. And we can also see how multiple words which are similar will be similar, or the similarity score between two similar words will be higher, while the similarity score between the two different words or phrases can be lower. So we're going to perform some semantic analysis of multiple phrases and sentence using the Gemini word embeddings, and we'll actually see this practically how it happens. So whatever we have seen here is currently very theoretical, but moving forward, we'll see practically how we can do that, and we can understand how word embeddings models these words, phrases, or sentence in the higher dimensional vector space. Now let's move forward and see the introduction piece. So what the introduction mentions is, in natural language processing, a word embedding is a representation of a word. The embedding is used in text analysis, and typically the representation is a real valued vector that encodes the meaning of the word in such a way that the words that are closer in the vector space are expected to be similar in meaning. And that's what we discussed at the earlier, right? So we mentioned, or we discussed, that two words which are similar are kept together in the vector space, while the words which are very different from each other are kept far away in the vector space. So that's what the introduction pretty much covers, right? Now let's talk about the Gemini embeddings. These are the embedding models which is created by Google, obviously, and it is created through the Gemini model. So these embeddings are trained on the Gemini model. So once the Gemini large language model trains it, the Gemini embedding learns and tries to understand the vector embeddings and the semantics of the words, phrases, and the sentences, right? And Gemini embedding is a state-of-the-art embedding model leveraging the power of Gemini, Google's most capable large language model. And here in the diagram, you'll see on the left side, I have attached a paper of Google DeepMind, which is actually a technical report of the Gemini embedding when it was launched. And on the right side, it shows how these embeddings tries to map multilingual words in a dimension space together. So you'll see um, some pet words are there in different languages, I guess in English, Hindi, and maybe I guess in Chinese, some language like that. And it is trying to map these words into the vector embeddings. You can think of these dots as the numbers, and this is a series of numbers, and they're trying to map these words as a vector embeddings in the space. And hopefully they are trying to keep these words which is very similar closer to each other, despite of these are in different languages, right? And if I want to show you the paper, this is what the paper is. If I'll scroll up and zoom out a bit, yep, so this is a paper, Gemini Embeddings, Generalizable Embeddings from Gemini. So I'll basically attach the link to this paper in this video, so you can see it and read through it. This is a pretty long paper, so I'll not go through it. I'll just go on to the introduction piece. So basically in this report, we introduce Gemini Embeddings, a state-of-the-art embedding model leveraging the power of Gemini, Google's most capable large language model. And capitalizing on Gemini's inherent multilingual and code understanding capabilities, Gemini Embedding produces highly generalizable embeddings for text spanning numerous language and textual modalities. So what they are mentioning is that these embedding models, which they are calling as Gemini embedding models, because they are trained on the Gemini large language model architecture, and they understand multilingual text modalities and languages. So they have the capability to understand text given in different languages, and they can perform semantic analysis or multiple other things through that. And you can go through the paper. There are some performance analysis attached in the paper on the MTEB multilingual dataset. And actually the interesting thing to see is they are performing different kinds of analysis or tasks, and they are scoring the Gemini embedding model against different other embedding models as well, like Qwen2, Gecko, multilingual E5 large instruct, text embedding 3 large, different models. And you can see different types of tasks they have done. They have done classification, they have done clustering, they have done instruction retrieval, they have done multi-level class, they have done re-ranking, they have done retrieval. A lot of tasks are there, and the scores are also mentioned. You can go through it, you can skim through the paper, you can see the architecture and a lot of stuff. And I'll not go deep into the paper. We can come back to the agenda of this video, and let's go for it. So this is what we're gonna explore, or basically we're gonna practically import the Gemini embedding model, and we'll see how you can perform semantic analysis. And if I scroll down, you can use the Gemini embedding model to perform different tasks. I have noted 5 of the important ones. The first one is the semantic similarity, which we will be doing. So basically, given a word or given multiple words, the Gemini embedding models can perform the semantic similarity, meaning they can understand how different words or phrases or sentences are similar, or basically whether the semantic meaning of these phrases or words are similar or closer or not. You can perform question answering. Given a document, you can maybe ask some questions, and embedding model should provide the answer. You can also perform document retrieval. Given a particular phrase, you can get the topmost document, the way we do for RAG, retrieval augmented generation. We can perform clustering, we can perform text classification. So these are the tasks which you can perform through the Gemini embedding model. Now, for our agenda, what we are doing semantic analysis with Gemini embeddings, and we can use Gemini embedding model to understand and visualize the semantic similarity between two words, phrases, or sentences, right? So keep in mind, this is not only for words, it can use for sentences or phrases as well. And we can understand the semantic similarity between multiple words, phrases, or sentences. And how we can do that? So the Gemini embedding models will give you the vector, and with the provided vectors for maybe two words which or two phrases which you are trying to compare, you can perform cosine similarity or dot product or Euclidean distance between those two vector embeddings or vector representations, and you can get a score or a similarity ranking, right? And depending upon the score, you can decide how closer are the two words or phrases or sentences. So suppose if two phrases have a you get the vector embeddings from the Gemini embedding model for two phrases, and then you gave those two vector embedding representation to a cosine similarity, or you perform cosine similarity between these two vector embeddings, and you get a very high similarity score. Then you can expect that these two phrases or words are very similar, right? And you can not only perform cosine similarity, there are multiple other matrix which you can send the vector embeddings to get the similarity ranking. So dot product and Euclidean distance are also one of those matrix. For this session, we'll use cosine similarity, and cosine similarity is actually a measure of similarity between two non-zero vectors defined in an inner product space, and the cosine similarity is the cosine of the angle between the two vectors. So you can think of this as two vectors representing a particular direction in a higher dimensional space, and you can think of the cos of the angle between the two vectors to be the cosine similarity, right? So I guess the closer the two lines, the similar the two vectors are, right? On the right side, there is a diagram of the cosine similarity representation. On the left side, there is the vector representation of phrases or sentences in the two-dimensional space here. So you can think a man is walking, a little boy is running, a little boy is walking, a sad boy is walking, how these sentences are placed together in a vector space. Now look at my little cat and look how sad my cat is clustered together closer in the vector space, right? And this is how it shows how effective an embedding space, or how effective an embedding model can actually be if you want to perform semantic analysis for a phrase or a sentence or a word, right? And that's what we're gonna do. And now this is time for code walkthrough, where we actually go to the Python notebook and we'll see how we can pull these models and perform semantic analysis. So let's do that. Okay, so now we are at the code walkthrough and we'll see whatever we have discussed in the theory now here practically. So what we are doing here is that I have a Python notebook prepared, and this is not very complex. So this is just for a POC, and you can use this POC to build more complex things. So what we're gonna do, as we used to do always, we're gonna import the open libraries. So what I'm using here is I'm using the Google Gemini SDK. You just need to install that using pip install command, and then you will have actually access to all the Gemini libraries provided by Google, since these are open source. You'll need an API key for that, and that should be available on Google Cloud. So you can like create your account on the cloud and you can get an API key so that you can successfully call the models. You can easily find the documentation for all of this on Google. So what I'm going to do is that I'm going to load my environment variables, and I'm going to also load the client. So once I have the client, I can use this client to load the large language model or the embedding model, and I can basically talk to them, or I can basically send some request and get a response for it. So I have defined the client. Now what I'm gonna do is that I'm gonna use this client to load my embedding models, or basically from the embedding model I'll basically get the word embeddings for it. So we have discussed earlier that for a particular word or a phrase or a sentence, what a word embedding does, it provides an embedding or a series of numbers or a vectors for that particular phrase, sentence, or a word. And that's what actually we'll get when I'll query client.model.embed content, and I'll provide the model to be Gemini Embedding 001 model, which we talked about and which we discussed in the paper as well. So the paper, the technical report which we discussed earlier, was for this embedding model. In the contents, we are providing the word. So the interesting thing to note here is the contents can take a single word or a bunch of words. So if you'll give multiple words or an array of word or phrases or sentence, it will gonna give you the array of vector embedding. So you can, if you want to calculate word embedding for maybe 5 to 10 phrases, sentences, or words, or maybe more, then you don't need to like initiate the client model multiple times and get the request, get the response, or get the vector embedding one by one. It will take a lot of time. So you can just club all your phrases in an array, and then you can send it off to the Gemini model, and you can get the responses in bulk together at once, right? So that is one optimization idea you should always keep in mind. So here the word I am sending out is healthcare, and I'll get the vector embeddings when I'll gonna initiate this, and the vector embeddings will be stored here. So the response will give an array of embeddings where I'll have multiple embeddings. Now the fact that I have given only one word or a phrase, the size of the embeddings will be 1, so I can get the first embedding, the first vector embedding will be the embedding of my word, so I can directly extract that, and the embedding will be present in the values. So if I quickly run this, I should get the embeddings. And the first thing we can do is that we can check what is the length of the vector embeddings which we have received. So if I run this, this is the length of the vector embeddings, that is 3072. Now we have discussed at the start is that the number of vectors or the real numbers present in the vector embedding is equivalent to the dimension of your embedding model. So here is 3072, meaning the Gemini Embedding 001 model has a dimension of 3072. So it is using 3072 real numbers or vectors to represent each word, phrase, or sentences. So it is represented in a 3072 dimensional hyperspace, right? And I can also visualize these embeddings. So I'm not going to visualize all 3072. Let's visualize the first 20 embeddings, and we'll obviously get a series of numbers. This is how it will look like. You can see the 20 numbers here. Uh, like that, there are 3072 numbers. I'm not gonna flood my notebook here, but you get a gist of it, I hope. Okay, so this is one thing. Now we have also talked about the cosine similarity because we want to compare how two words are similar to. So for calculating the cosine similarity, I have defined, or I have implemented the cosine similarity in Python. What we are doing is that we are performing the dot product, and then we are dividing the dot product with the dot, or with the product of the two vectors, right? So this is what we are doing here, and we are taking these two vector representations as input, and this method should represent the cosine similarity score in return. So I'm gonna define this method so that we can reuse it in future. Now the second thing we are doing is that we are taking the embedding for a particular word. Now for this time, let's take word 2. So I'm gonna comment out word 3 so that it doesn't get, I don't accidentally use it in this walkthrough. Okay, so for now we have word 2, which is let me correct the typo, which is medical insurance, right? And I'll get the response or the vector embeddings for word 2, and I can see, like I can store this embedding here. So if I run this, I'll get the word embedding or phrase embedding for the phrase medical insurance. So the word embedding is present here. Now I can perform the cosine similarity to see how similar these two words are. Now I am performing the cosine similarity between word embedding and word embedding 2. So you can think of it, we have already shown above that the word embedding 1, or the word embedding, actually is for healthcare, and word embedding 2 here is for medical insurance. So you know that word 1, the one which we mentioned above, is healthcare and medical insurance. So healthcare and medical insurance are very close, or like the semantic meaning of these two words should be closer, because these two represent a healthcare space, right? So healthcare and medical insurance, I'll expect that the cosine similarity between these two word embedding should be higher than any other different embedding, right? So I can calculate so let's do that. Let's calculate the cosine similarity between healthcare and medical insurance, and when I'll run this, I'll get a number which is 0.64. So you can think of this as the word embedding between these two. So let me quickly write it here: medical insurance, and here we have healthcare. Okay, so between medical insurance and healthcare, we got a cosine similarity of, let's say, 64.269, so 27%. This is the cosine similarity between these two. Now let's think about an interesting thing here, and let's see. Let's take another word, which is customer care. Now there is a reason I am taking this word, and we're gonna compare it with healthcare, right? And we'll expect a lower word embedding because the word healthcare and the word customer care is different. So you can think of customer care as a customer support, or related to customer support or customer service, but healthcare should be related to the medical or a health space, right? Now the thing is, these two phrases have a common word, care, right? So if the embedding model is actually understanding the semantic of these two phrases, even though these two phrases have a similar word, care, it shouldn't put these two phrases together, because even though they have a similar word, care, but the semantic meaning of these two phrases are very different. And that's why I'll expect a lower cosine similarity score. Now to prove that, let me quickly run this. So instead of word 2, or basically I'll use word 3, and here I'll use word 3. So I'll put word 3. So this time in here we'll get the response for the embedding for customer care. Okay, now let me quickly run this one and I'll get the embedding stored here. Now I have the embedding. I can again run the cosine similarity to see now what is the similarity score we have got. So the similarity score we have got is 57.45%, right? Now this is the one. So even though they have similar words, the cosine similarity of customer care is lower than the cosine similarity score between medical insurance and healthcare, right? And maybe we can experiment with one more phrase and let's see what happens. So this time I'll again take healthcare as a common phrase, but this time let me map it with hospital hospital care maybe, and let's see what similarity score we'll get this time. So instead of customer care, I'll just replace it with hospital care, and I'll comment this word out, and I'll run this. I'll get a embedding for hospital care. And if I run the similarity score, again I'm getting a very high similarity score because hospital care and healthcare are very closer or very close, the semantic meaning of hospital care and healthcare is very similar to each other. That's why I'm getting a similarity score here of 69%, let's say 16 point maybe 0.5% here. Now this is a higher similarity score as compared to the other one, right? And that makes sense. And here the fact that this is providing the similarity score on the basis of their semantic, we can think of this model is actually, or this embedding model is actually understanding the semantics of the words, phrases, or sentences we give them. So we can perform clustering, classification, semantic analysis, and multiple different other activities using this model. So this was it in the vector embeddings or word embeddings. I hope now you have a clearer and better understanding of what vector embeddings or word embeddings are in the context of natural language processing. I also hope that you now should be able to take a word embedding uh, from any provider, and you can use them for semantic analysis or other different tasks which we talked about. Now, this is, I guess, 11th or 12th episode in the AI Engineering 101 playlist, which we are building here. And if you haven't checked out, you should actually check out other videos in this playlist. We have talked about building agentic workflows from scratch. We have talked about multiple concepts involving AI engineering from scratch. We have also done the code walkthrough and actually built them from scratch. And all the code walkthroughs which we have done, the link to the code is always present in the description of the video. You can check that out as well. And the code walkthrough for this video also is present in the link to the description of this video. You can check it out. The paper which we have talked about, the technical report of Gemini Embedding Model, is also linked in this video. You can check that out as well. And if you found this video insightful, do like this video, share it with others, and subscribe to the channel, and I'll meet you in the next video.